crazy because he doesn't even get that famous mask until the third movie.
I didn't know that.
The first movie was his mom was killing everyone. The second, he had a bag over his head with eye holes.
It became iconic. All right, welcome everybody. Wednesday class is online. We won't meet together in this classroom on Wednesday. It's just going to be a recorded lecture video for that day. Friday we'll be back to normal though. The homework number 2 is due on Wednesday, and we're going to do an example in the second part of today's class that I think may help you with one of the homework problems. But for the first part of the class, all we're going to do is a comparison between the 3 friction loss methods that we've talked about so far and get a chance to see how the easy Manning's and Hazen-Williams equation stack up when compared to the Darcy-Weisbach equation, which I've told you before is kind of the gold standard in terms of accuracy and estimating friction loss in a pipe. So before we start with today's material, are there any questions related to the announcements? Where or when? When. When I tell you we are. We're going to continue with our 3 o'clock time until further notice. So, yeah. I've got the same incentive as everybody else. I'd like to make it as soon as possible, but there's a lot of turmoil right now with the reorganization of the college, and so, yeah. So, Friday, 3 o'clock. Next week, who knows? But Friday, still 3 o'clock. All right? All right. Other questions? Okay. Let's do a comparison. Let's try as much as possible to use the same kind of criteria for the 3 different methods, Hazen-Williams, Manning's, and Darcy-Weisbach, and ductile iron pipe. And so what I've done is I've found the C sub H value that would correspond to a ductile iron pipe, Manning's N for a ductile iron pipe, and then the equivalent sand roughness for ductile iron pipe, 0.26 millimeters. Let's find out if we had a flow velocity of 1 meter per second and the pipe diameter is 150 millimeters, then over the course of a 500 meter pipe length, what would be the head loss? And the units are going to be head loss in meters according to these 3 different methods. Now, of course, with the first 2, it's just direct substitution of the roughness coefficient. For the third, in the Darcy-Weisbach equation, you'll need to estimate the friction factor with this equation. Which one is this? Jane. Good. Yeah, this is not the Colebrook equation. It's the Jane equation, but Jane will be fine in these circumstances. It'll give us a good estimation of F value. Oh, I remembered one other thing. Now, the grader is going to be going through homework 1, which you've submitted already, right? I took an initial glance at homework 1, and many of you don't yet know how to read a Moody diagram. I was shocked at how many people got the wrong F value off the Moody diagram. So we may need to do like a remedial Moody diagram class where I print it out and go over it together, because we're not quite there yet. Luckily, this one you don't have to use that complicated Moody diagram. We'll just do the Jane equation instead. All right, so I'm going to pause the recording, give you some time to calculate H sub F according to these 3 different methods, and then let's see, if Darcy-Weisbach is the gold standard, how close does Manning and Hazen-Williams get to that gold standard? The first 2 are pretty easy, right? Hazen-Williams and Manning, since it's just a direct substitution. So Hazen-Williams should be 3.85 meters. Did everybody else get 3.85 meters as the head loss for Hazen-Williams? Yes. Yep. 3.85 meters for Hazen-Williams. Now Manning's equation likewise is pretty simple, but we get 6.73 meters. So, that's nearly double the head loss. And so the first 2 methods really don't agree very tightly. Of the 2, I would always say that the Hazen-Williams equation is going to do better for pipe flow than Manning's equation. Manning's equation, its specialty is open channel flow, where there is there's some part of the water that's not in contact with a wetted perimeter. So the reason why Manning's equation is exaggerating the head loss is it's really intended for flow that's open to the atmosphere at the top, where there's going to be less contact with a surface that's providing resistance. Now, in the Darcy-Weisbach equation, what we have to do first of all is calculate the Reynolds number, because that's going to go into the Jane equation. So remember, in Reynolds number, it's a velocity, a length parameter, and divided by the kinematic viscosity. We have two length parameters in our problem statement. We have a diameter and a distance. And so it's the pipe diameter that we put into the Reynolds number. So 1 meter per second, 0.15 meters, and then the kinematic viscosity. Reynolds number is unitless. And the other thing that's unitless is the ratio K sub S to D. We're going to be adding together two unitless terms. And for K sub S to D to be unitless, it means that we have to have both of them either in millimeters or both of them in meters. And so here we put the D was 0.15 meters, but when we're in the Jane equation, the substitution is going to be 150 millimeters for the diameter and 0.26 millimeters for the equivalent sand roughness. So if you do the Jane equation correctly, you should get that the F value is 0.024. And then from there, the substitution becomes relatively direct. The correct friction loss estimate is 4.08 meters. And so of the two, Hazen-Williams equation is a lot closer than the Manning's equation was. And the reason why Hazen-Williams equation is better is it's an empirical equation that's calibrated to closer conditions. It's for the range of velocities, pipe diameters, water temperatures, and enclosed flow that are also applicable for Darcy-Weisbach. It's just that in Darcy-Weisbach, the friction factor F is dynamic, whereas it's static. It's just the single C sub H value for the Hazen-Williams equation. This C sub H value doesn't change as the velocity varies. All right. So any questions on that example before we move on to the next? All right, let's consider the case of an elevated tank that we're pumping water to. So here's a pump that's lifting the water, total elevation of 35 feet. So it's lifting it from a lower reservoir to an upper reservoir. So what work is the pump doing? Well, the pump is doing the work of the lifting, so the delta Z, but the pump is also doing the work of overcoming friction. And in this problem, it tells us what flow rate we want to achieve. We're using a 10 horsepower pump to do the work, and it's flowing through a pipe length of 800 feet. We have the equivalent sand roughness for cast iron. So what diameter is needed so that we can achieve this flow rate with a 10 horsepower pump? Now horsepower is, obviously we're in traditional units for this problem, and so here's all the applicable equations we're going to use. First of all, the relationship between horsepower and pump head for a certain unit weight and flow rate. So that's essentially the power equation that we saw in fluid mechanics. The power equation was just gamma times Q times HP if we wanted watts for power. But if we have pounds per cubic foot for the gamma and cubic feet per second for the Q, and if the pump head is in terms of feet, and then we divide foot-pounds per second by 550, then we get horsepower out of that. So this is both the power equation and the units conversion from foot-pounds per second into horsepower. That's this lower right equation. Of course, the kinematic viscosity that's at the tip of my tongue all the time, 1 times 10 to the minus 6th, that's for SI units. In traditional units, it's a little bit different. And by the way, I got a good question this morning about your textbook. Your textbook has a printing error in Chapter 2, right? Which table was that? Do you remember the table number? It's the table that has fluid properties. It has the SI fluid properties at the top and the traditional unit fluid properties down below. And they just made a mistake and they say SI when really, they say degrees Celsius when they meant Fahrenheit. So just be aware that your fluid properties table in our hydraulics textbook, I mean, all the values are correct and all the column titles are correct. It's just the lower table, which is traditional units, they accidentally said Celsius when really it's Fahrenheit. Okay, so anyways, since we're working in Fahrenheit, these are this is the kinematic viscosity value that we're going to use. Okay, so what pipe diameter is needed? This is the equation that we've seen before, but we've only used it when it was free flow, like when the water was flowing from some upper reservoir to a lower reservoir, and then we already knew the H sub F. Do you remember how we knew the H sub F when we were working, for example, let's go to one of those examples. This one. How did we know the H sub F?
Change in height.
It's the change in height, because we know, how much energy is there at the beginning versus at the end. And that's the definition of H sub F, it's the change in energy. We're losing energy because of the elevation and the pipe friction. And so since we know the elevation of both these locations, then the only factor that was remaining between the total energy at both locations was the H sub F. So it's a little bit different in this next example that we're doing today, though, because it's not just the elevation difference. Now there's also the pump that's adding energy. So the first step of this problem is applying the energy equation between the two locations. Location 1 will be our origin here at the lower reservoir, and location 2 is going to be the water surface at the upper reservoir. So let me write that on the board. The first thing that we're doing is we are considering the energy equation, and we're going to cancel out the terms that don't apply. Okay, so P1 divided by gamma plus Z1 plus V1 squared divided by 2G plus H sub P. This time we do have a pump, so oftentimes we write the energy equation without pump head. This time we're going to include it. Equals P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus H sub F. Okay, so now look at the sketch. At location 1, the surface of the reservoir, the water isn't pressurized, so I cancel out the P1 term. At the destination reservoir, at the surface of the tank, the water isn't pressurized, so I cancel out the P2 term. At both of those locations, it's just water in a tank. Static conditions, the water's not flowing inside the tank at the surface. The water is flowing through the pipe, but here where it says V1, that means what is the velocity of the water at location 1? In the surface of that reservoir, it's 0. So I cancel out both of the V1 and V2 terms. And so all we end up with then is, let's call Z1, let's make our elevation datum be the water surface on the left. So Z1 is 0. So therefore, HP is Z2 plus H sub F. So how much pump head do we have to add? We have to add the elevation difference, 35 feet of head, plus however much friction loss there is. And we don't know that yet. We're going to calculate that. How much friction loss is there when you are pumping 1.5 cubic feet per second through a pipe? We don't yet know the pipe diameter, so it's going to be something that we have to iterate. So does everybody understand where we're at so far? The scenario, the setup here is we know the pipe's size, we know the pipe length, we know the the pump power, and we're going to try and find out what pipe diameter is needed. So if you've got Excel available, you can follow along. We're just going to start a spreadsheet here where we try and iterate and find the diameter required. Let me paste this equation so that it's here on the screen. And I'll also paste in the Jane equation so it's at the ready when we want it. Okay. So some preliminary stuff. Horsepower. From the problem statement we know it's 10 horsepower. And the cast iron K sub S. So cast iron K sub S in feet. I think in the problem statement we're told that that is, let's just double check here, 0.00085. So 0.00085 feet. And then the unit weight in terms of pounds per cubic foot. And our typical unit weight for water in those units is 62.4 pounds per cubic foot. Another factor is kinematic viscosity. And the units there are feet squared per second. And the kinematic viscosity of water at this temperature is 1.22 times 10 to the minus fifth. Okay, so 1.22 E minus 5. Okay, and it understands that as a scientific notation. And our flow rate Q in terms of cubic feet per second. The problem statement says we want to achieve 1.5 cubic feet per second. All right. And the H sub P, this is the pump head in terms of feet. Let's do the pump equation with this. We'll rearrange to solve for H sub P. Excuse me, solve for H sub P with the horsepower that's known. So we rearrange that equation for the horsepower. We get H sub P, which is pump head, is going to be 550 times the horsepower divided by gamma times Q. Okay, so that's 550 times the horsepower, which is 10 horsepower, divided by 62.4, multiplied by 1.5 CFS. All right, so the pump head that's required, I'm just now solving that. 550 times 10 divided by 62.4 divided by 1.5. 58.7 is the pump head that we have to be adding. Okay. I guess that's how much pump head can be achieved with a 10 horsepower pump at that flow rate. So that's kind of our currency. That's how much energy is being added. Now, how much of that energy is getting used for the lift? 35 feet is going to be getting used for the lift. And so that tells us how much is left over to spend on the pipe friction. So H sub F, in terms of feet, is going to be the amount of energy that is being added by the pump minus the elevation difference of, what's our elevation difference? 35 feet. Okay, so 23.76 is left over to overcome pipe friction. The pump's adding 58, 35 of it is the delta Z, and so this is how much energy we have for the pipe friction. Now we'll just have here our G value in terms of foot per second squared, 32.2, and then our pipe length in terms of feet is 800. All right. So our first iteration. Now, why do we have to iterate? Can't we just... The question, the overall question that's being asked is, what diameter of pipe is needed? Here's the equation for it. Why don't we just start solving that now?
You don't know F, do you?
We don't know F. So we have to answer the question, what the F? Chain equation will tell us what's the friction factor.
What the F?
Puns are the lowest form of humor, right? Puns. All right. So, okay, so what should we use as the F value? Why can't we find the F value right away? What don't we know in this equation? So in this equation, we don't know F. What don't we know in this equation? Okay, but let's... Oh yeah, you're right. We don't know diameter, right? What else don't we know? That's only one of two things we don't know. We don't know Reynolds number. How come? Because it depends on velocity, which depends on diameter. So we're in a tricky spot here, but we'll just start with a guess. Like, what if, I don't know, maybe we'll say F. I'm going to write this, begin with the guess. So maybe F equals, and I'm not even going to make it a particularly good guess. Like a good middle-of-the-road guess would be 0.02. 0.01 isn't an especially good guess, but it's just to show you that we can converge to the right answer even with a guess that's initially not so great. Okay, so if that was our F value, what would be the diameter? All right, so this diameter in feet is now going to be based on the guess value of F. Okay, so it's equals 8 times length. I'll reference that with F4 so that it's locked, times Q, lock, and raise it to the 2 power, okay, times F. This time I'm not going to lock the reference because I want to be able to copy and paste later on as I iterate. But now I'm going to divide by H sub F, anchor the reference, times G, anchor the reference, times pi squared, so pi parentheses, close parentheses, to the power of 2. Now I'm doing a parentheses to close out the denominator. Now the next parentheses will close out this, these brackets, and now it needs to be to the power of 0.2, or 1 divided by 5. All right. So this diameter it's going to tell me is that's the diameter that would be needed if the F value was 0.01. And so it's saying if the diameter was 0.01, then you'd need a pipe that's 0.45 meters in diameter. Okay. Now that I have a diameter, let's find out, well, with that diameter, what is the area in terms of square feet? Because we're going to check the guess. You never make a guess without checking to see if it was good. And so, to check and see is it good, we have to know the Reynolds number. And to know the Reynolds number, we have to know the velocity. To know the velocity, we have to know the area. So it's a whole chain of events here. So any questions so far? Jeffrey, do you have a question?
Oh, I got 0.138 on the temporary diameter.
That's not the right value.
I know, I'm trying that one out.
All right. We're not particularly pressed. Okay, so what is the area with that diameter? So pi times d squared divided by 4. Okay, that's the area. And I just think it's nonsense to have too many significant digits showing. It just clutters things up. So With that's the area, then what's the velocity? Okay, how do we get the velocity?
The flow rate divided by the area.
Good. Be sure and anchor the reference to the flow rate so that when we copy and paste later on, it's always looking up at the right spot. Okay. So that is our velocity in this grand what if. Now if we know the velocity, we can calculate the Reynolds number. The Reynolds number is unitless. So Reynolds number, remember, is V times D, and we're using this D that we've calculated, divided by the kinematic viscosity. Anchor the reference so it's always looking up there at the right location. All right, so that's the Reynolds number. Now, next time we do this, we don't have to guess. Now, calculate F with Jane. Okay, so F equals, now I'm not just going to pull a number out of thin air, I'm going to use this. So F equals 1.325 divided by the logarithm of K sub S, where's that? Here, anchor the reference, divided by 3.7 divided by diameter. Which diameter? Let's use our most recent diameter. The best diameter that we know so far was this one. And gradually it'll converge. But for now, that's the best idea of what we have for what the diameter is. Plus 5.74 divided by the Reynolds number. Well, what's our best Reynolds number guess? This one. To the 0.9 power. And I start closing the parentheses, and then it's to the power of 2. So this F value is going to be better than a guess, but it's not going to be great because it's based on a diameter and Reynolds number that was based on a guess. So it's kind of like one step removed from just a flat-out guess. But the more times we do this, the closer and closer it's going to get from iteration to iteration. It's called convergence, where the numbers aren't changing so much and it kind of stabilizes on a solution. That's what we're aiming for. So we calculate this new F value. Let me express that. I want to see it, not scientific, just general. Okay, so instead of 0.01, now it's saying 0.0237. Good. All right, now this is the fun part. You just highlight all of that, Control C, put it down here, Control V, and what it's doing is it's giving us a new guess of the diameter, and based on that, let's just look at, did it reference all the important stuff at the top, the constants? Yes, but the new F is what it's using. So it's all the same factors that were constant as before, but now it's looking at the new F that we just estimated with the Jane equation. And so we'd already had the formulas for area, velocity, Reynolds number, so we don't have to type them in again. We just do that, highlight, select, Control C for copy, Control V for paste, and all those things are dynamically iterated. All right, so are we done? Well, if we go from a diameter of 0.45 to 0.53, that's a big change. I want it to be changing less than 1% from iteration to iteration. So we haven't yet hit the threshold where the diameter is hardly changing anymore. So I'm going to call this, this was our first guess. This was calculate F with Jane. Let's call it iteration 1. Now, let's do the same thing. I'm going to copy all of it, and I'm going to paste. This time I'm going to call it, though, iteration 2. And everything is automatically calculated. We don't have to do any more work. So, what's the percent change, though? Diameter 0.53 to 0.53. It's getting nice and close. How about the F value? It's changing a little. since it takes us so little effort, we might as well continue until it really converges. So the answer is, like, what pipe diameter do we need? 0.535. 0.535. And we're getting a slightly different F value from step to step. But now it's converged well enough that any slight adjustment in the F value is no longer having an effect on the pipe size that's required. So what pipe diameter is needed? We need a 535 millimeter pipe. All right. No. I guess that's 53 millimeters. Yeah, is that right? Yeah, there's 1,000 millimeters in a... You made me second guess myself. All right. Other questions? Do they sell 535 millimeter pipe?
No.
It's pretty definitive. That's a no.
Well, I doubt.
I don't think so. It seems unlikely, right?
Unless you special order it.
Unless you special order. And think about how expensive that's going to be. So, all right, let's say, what if we can't get that exact size pipe? What if they sell a 500 millimeter pipe or a 600 millimeter pipe? So what if we bought the 500 millimeter pipe and we put it in this system? What's going to happen?
Wait, wouldn't this be in feet because everything else was in feet?
You're right. Yep. You were right. I was wrong. It's not millimeters. This is feet. So this is diameter in feet. Okay, so let's see. What's this times 12? Inches. All right. Inches. How come the rest of you didn't catch that? I was just so confident about it being millimeters. Yeah. Don't let the ramblings of a madman question your ability to second guess. All right, so what pipe is needed? 0.535 feet. They don't make pipe that size. They do make a 6-inch pipe and an 8-inch pipe is available. Okay, your client doesn't know hydraulics, but they do know that a 6-inch pipe is cheaper than an 8-inch pipe. They ask you, what happens if we just buy the 6-inch pipe? So in this system, what if they just use the 6-inch pipe? What is the consequence going to be? Let me give you a hint. The pump isn't going to catch on fire. It's not like the pump breaks.
Is it less pressure? Or no, we don't.
We never calculated pressures.
Yeah.
Did somebody over here? Too much what? So you're saying that the flow rate's going to change? Okay, so you're right that the flow rate's going to change, but if it's a 6-inch pipe and what we really need is a 6.4-inch pipe, how is the smaller pipe going to change things? Remember, what does a small pipe do compared to a big pipe?
It increases pressure.
Well, the velocity is going to change, like if you just think about Q equals VA, but think about resistance. How does having a smaller pipe affect the resistance?
There's more resistance.
There's more resistance when you try to get the same flow rate through a smaller pipe. So the answer is, if you use this pipe, the Q will be less than the 1.5 CFS that is needed. You won't be able to achieve the flow rate that they need. If you use the bigger pipe, then you will get more than 1.5 CFS. So if they really only want 1.5 CFS, then your answer is use the 8-inch pipe and put a valve in. Because you can close the valve down a little bit and control the flow rate from there. By closing the valve, you're just introducing a little bit more head loss. This time, instead of due to pipe friction, it's a local loss. But that 6-inch pipe isn't going to achieve 1.5 CFS unless the pipe length is shorter or the lift distance is less or if it was smoother. All right, so hopefully with that it sets you up to do well on the homework problem that's related. Remember, what were our steps here? First was the energy equation. We analyze the energy equation to find out, if we've got a certain amount of pump head that we can generate, how much is left over for the H sub F, the pipe friction. And then our iteration process was with all of these constants, we don't know the F value, so we have to start with a guess. And we just kind of over and over until the F value wasn't changing anymore and until the diameter wasn't changing anymore. We kept solving until we found out the pipe size that's required. All right. Any questions about the illustration? I suggest you save that in case it's useful on the homework or something like that. Let's take one last look at these announcements before we finish a few minutes early. Remember, class on Wednesday is online. We'll meet at our normal 3 o'clock time in this location on Friday. All right. Have a good day.